Welcome to the new unit on transformations. On the first page of your note package, you can see that there are a bunch of graphs. Some will look familiar to you, some of them won't. For example, we've seen the constant graph, the linear graph, absolute value, the quadratic, the cubic, the square root, maybe even the cube root. The trig functions, we will be learning those when we do our trigonometry unit. The reasons why I am showing you these graphs again is because we will perform transformations on them, meaning that we're either going to stretch or compress them horizontally or vertically. You can also shift them up and down or left and right. Our first lesson is just going to focus on the horizontal and vertical transformations, which is probably the easiest type of transformations. So your rules for the horizontal translation, our rule is to let f of x be the original function and h be a constant. Then if you have f of x plus h, this means you translate f of x to the left h units, and f of x minus h means you translate f of x to the right h units. So if you see a plus here, it means we're going to move to the left. If you see a minus in between, it means we're going to move to the right. So for our first example, we have the translation f of x minus 3, where original function is x squared. Since we have a minus 3, that means we're going to translate to the right by 3 units. Okay, so I'm going to graph just our x squared here, my standard x squared graph. Now my new graph is just going to be the same graph, but move all those points 3 to the right. So my vertex used to be at 0, 0. I can move it over 3 to the right. 1, 2, 3. That is my new vertex. At a point here, move it over 1, 2, 3, 1, 2, 3. This is my new point. So you can do that for all of them. And this is what you get. So this light blue one is our f of x minus 3. The dark blue one is f of x. So that's one method of translating by just looking at your points and moving them directly where they need to go. This is okay if we have an easy transformation to do. Sometimes you're going to be given really long transformations that this is not going to be the only transformation you need to make. So I'm going to show you a way how to do it almost algebraically, and then you can utilize this when you have much more in the future. So xy is your standard xy points on f of x. Now our transform graph, we're going to move every x value over to the right. In other words, I'm adding 3 to x. And the y value didn't change. So if I start off with the vertex of 0, 0, this means my new graph is going to be 0 plus 3 as my x coordinate. My y value is going to be still 0. So that's why I had a point at 3, 0. Let's just say I had a point at 1, 1 for my x squared graph. If I want to do the transformation, that is 1 plus 3. My y value is still 1, so that I have a point at 4, 1. So you can do that for all the other points to figure out what your new points are going to be. Moving on to example 2. It was kind of confusing here because we have this negative, negative. But I can rewrite g of x as absolute value of x plus 2 once I open up that bracket, and we'll have a double negative. It becomes a positive. So it says give the name of the original function and describe the transformation and then sketch. So this is the transformed function. I want to find the original. Well, the original is just going to be your absolute value function, the absolute value of x. So f of x is equal to absolute value of x, which is the absolute value function. This is our translated graph. And if we want to describe this, because it says describe, we're going to use our words to do that. Because we have a plus here, this means we're moving to the left, and we're moving to the left by 2. So that is how you describe the transformation. And we're going to graph our translated graph. Usually we would have a point at 0, 0, but if I move to the left by 2, I have a point at -2, 0. And I create my rest of the graph here. There's your absolute value function for g of x. Moving on to vertical translations. For vertical translations, k is a constant that's outside of the f of x. And when you see that, this plus k means you're going to move up k units. Negative k means you translate down k units. Our original graph is x squared. Let me go ahead and graph that in there. This plus 2 means we're going to move up 2. So that means my vertex that was at 0, 0, I'm going to move up 2, which is at 0, 2. At a point here at 1, 1, now it's going to be at 1, 3. And that is our graph there. Again, you could also do this algebraically. So we'll start off with just your normal x and y from the original graph. We're doing nothing to our x value, we're not moving it left or right, but we are moving up our y value by 2, so this will be y plus 2. So if at a point at 0, 0, this means my new point is going to be at 0, and then 0 plus 2, which is a point at 0, 2. And we can do just one more just to make sure we understand this. If let's say I point at 1, 1 from x squared, my new point is going to be at 1. My y is at 1 plus 2, which means we have a point at 1, 3. Let's look at the next example. So it says, let g of x be x squared plus 6. Give the name of the original function and then describe the transformation. So you can tell that the original function is your quadratic, which is x squared. And this plus 6 means that we went up 6. And our function for g of x is x squared plus 6. So we just grabbed the transformation because we already said we're going up 6, and now we're going to sketch it. So we have a point at 0, 6, and a point at 1, 7, negative 1, 7. And if you didn't know those were the points, you can always use a table of values so you can figure out some points. And that is your graph. In this next example, we're going to do two transformations. We're going to move to the left because we have a positive 4 here. And then we're going to move down 8. So let's just draw our x squared graph first. And now I'll perform the transformation. So what you can do, there's two options to this. You can just do it by looking at it, because we know we have to move to the left by 4. So your vertex is going to go 1, 2, 3, 4, and then down 8. 1, 2, 3, 4, 5, 6, 7, 8. So this would be your new vertex. And then you do the same for every other point. And that would be your graph. Another option is doing it a bit algebraically. So we're going to move to the left by 4. That means we're going to go to the negative side, so x minus 4. We're going to go down by 8, so that'll be y minus 8. Get a point at 0, 0. We can use another point at 1, 1. So that's going to be 0, negative 4. 0 minus 8, which is the point at negative 4, negative 8. And you do the same thing for another one. 1 minus 4, 1 minus 8, which means your new point is at negative 3, negative 7. And then you can do it for more points if you need. But otherwise, yes, you can also do it right on the graph and just count down and count to the left. In our next example, we're given the graph y equals root x. Apparently it's translated 2 units to the right and 1 down. We want to find the equation of the image graph. So this 2 units to the right, this affects the x. And 1 unit down, this affects the y. And how does it affect the x? We're going to go 2 to the right, which means it would be a minus 2 to go to the right. So if it's right, it's minus. And then to go down, that's also minus, minus 1. So our graph is the root of x. I need to put in this negative 2, which affects the x. So it's going to go inside the radical. And this negative 1 is on the outside of our function. And that would be the answer to the image graph. For example 7, describe how the graph of 1 over x could be translated to create y plus 1 is equal to 1 over x minus 2. And then find the equations of the asymptotes of each image graph. The first thing I'm going to do is rewrite this so that my y value, this plus 1, is on the other side. This is our descriptive form when we were drawing our rational graphs. But if we think about how transformations are being acted upon this, we have this 2, which means we're going to the right by 2 because it's attached to the x. And this negative 1 means we're going down by 1. So we can just state that in words because it says describe, and describe means we have to use words. We're going to go down 1 unit to the right by 2 units. And then our equations of the asymptote is we have a vertical asymptote and a horizontal asymptote. The vertical asymptote, we're going to look at our denominator to figure that out, and our denominator can never be 0. So if x was 2, that's when that would occur. So our VA is at x equals 2. Our HA is determined by this negative 1, which is going to be y equals negative 1.